Okay, thank you. So, in our previous lecture, we talked about double sideband suppressed carrier, and this method is better than the amplitude modulation method. The reason is that it saves 67% of the power by suppressing the carrier. We require carrier in amplitude modulation. It means a huge amount of power is lost in amplitude modulation. However, it is another additional advantage that amplitude modulation method is quite simple and robust method, but at the same time, it is more power consuming method. So to suppress that power, we have discussed the another method that is called as double sideband suppressed carrier. So in this method, the carrier is suppressed and 67% of the power is saved. And how this suppression is achieved mathematically, we have discussed in our previous lecture by discussing the Fourier transform and frequency shifting theorem, in which we multiply the modulating function or modulating signal with some exponential function, and that exponential function will increase or decrease the carrier frequency of the modulating signal. And finally, we obtained the expression for the double sideband suppressed carrier, and that expression involves xt as the modulating signal and cos omega ct as the another signal, but that is a suppressed carrier. With the help of a block diagram, we also discussed in our previous lecture that for double sideband suppressed carrier, we require a modulator. That modulator will involve the two inputs, that is cos omega ct and xt as the baseband of the modulating signal, and modulator will multiply the two functions, modulating signal as well as cos omega ct, and that modulated signal will involve suppressed carrier, and hence the name double sideband suppressed carrier. Now in today's lecture, we will talk how to generate this double sideband suppressed carrier. There are two methods. We have a linear modulator or the non-linear modulator. Linear modulator have a linear expression just like a straight line equation, y is equal to mx plus c, where x is an independent variable and y is a dependent variable, m is the slope and c is the intercept. So that relationship is a linear relationship between the y and x. So similarly, we will have a linear relationship between the gain function and the modulating signal. And this expression is G is equal to K times modulating signal, and K is the constant of proportionality. So the another method is using the non-linear modulators. We will discuss non-linear modulators later. So in case of a linear modulator, we will have a gain function which is nothing but our modulating signal xt. We will have an input which will act as a carrier cos omega ct. The modulator will try to multiply the two functions, and the two functions are the xt and the cos omega ct. K is the constant of proportionality. So the another representation of linear modulator is that we will give input from this side and cos omega ct from another side in the modulator, and we again have the same output, that the K times xt cos omega ct. So the output is written as V0, which is equal to gain times the input. Gain is this K into the modulating signal, input cos omega ct, and another input. So this is a linear response. Linear response means as the xt function increases, the output function increases. As the xt decreases, the output function decreases. This is called as the linear response. Now, what is the main advantage of this is that we can, by using these linear and non-linear modulators, we can suppress the carrier. And how the carrier is suppressed will be clear from the next slide, where in the block diagram we will explain how the carrier is suppressed. So, what basically the principle of operation is? The principle of operation of this suppression of the carrier is that whenever we fed two signals at different frequencies through a non-linear resistance, means through a non-linear electronic device. What is this non-linear electronic device? This is a semiconductor diode. This can be a junction field effect transistor JFET. This may be a BJT, that is bipolar junction transistor. So all these three are the non-linear devices and their resistance behavior is non-linear. So all those non-linear devices in which we feed the two signals at two different frequencies, then the carrier is suppressed in them. This is the basic principle of the double sideband suppressed carrier block diagram system. So let us see how this suppression of carrier actually happens. For the suppression of the carrier, we will have a message signal which is represented by xt. Now this message signal is fed into two separate modulators, in amplitude modulation modulator M1 as well as amplitude modulation modulator M2. But what is the difference between the two is that here we substitute a inverted modulating signal, that is minus xt, and this phase inversion is achieved by using some phase inverter, that is half wave or full wave rectifier. The rectifier's function is to introduce a phase difference into the signal. So basically these signals are nothing but the voltage or the current levels, voltage or current signals, because you know the voltage is written as V naught sine omega t, V naught cos omega t, and these are nothing but the sine cosine functions whose variation changes with respect to phase. Similarly, the current expressions are I naught sine omega t, I naught cos omega t. These are also the sinusoidal or cosine variable in phase. So these signals are nothing but your voltage or current levels, and their phase can be interchanged by using the phase changing devices, that is rectifiers, also half wave or full wave rectifiers. So message signal is fed as it is in modulator 1 with the phase inversion using a rectifier is fed into modulator 2, and these two modulators are fed with the carrier oscillator which will generate the carrier frequency, and this carrier signal is given by EC cos 2 pi fct. In place of writing 2 pi fc, we can also write omega c, that is angular frequency. Fc is the linear frequency. So when these linear frequencies are superimposed upon the message signal, then we know the process of modulation takes place, and this process of modulation will try to change the characteristic properties of the carrier wave. And what are these characteristic properties of carrier wave that are changed are the frequency, phase or amplitude. So correspondingly, when this carrier oscillator generates a carrier wave and these carrier waves are fed into the message signal modulator M1 and modulator M2, then these are superimposed and will try to change the characteristic properties of the carrier. So after this superimposition process, the two modulators will give the two outputs, S1T and S2T. These two outputs are separate and different from one another, and when these are passed through a adder or subtractor, we will get correspondingly the signal. If we use a subtractor, we get a double sideband suppressed carrier. So now let us use a subtractor in place where the two outputs from the two modulators after the modulation process are fed. Let us say output of M1 modulator is S1T, output of modulator M2 is S2T, which is equal to EC 1 plus MXT cos 2 pi FCT and 1 minus MXT cos 2 pi FCT. These plus and minus sign are because here our message signal is XT, which is fed directly as it is in modulator M1, and it is minus XT, which is obtained by phase inverters and is fed into modulator 2. So that's why here minus MXT. Now when these two outputs from M1 and M2 are fed into the subtractor, then subtractor will give a output after subtracting the one signal from the other. Let us say signal S2 is subtracted from signal S1, and in doing so, we can take this term EC cos 2 pi FCT, which is present in the both terms, both outputs from M1 M2. Then we get in bracket term 1 plus MXT minus 1 plus MXT. 1 get cancelled, and the output of the subtractor is 2MECXT cos 2 pi FCT, and this expression is free from the carrier. And that's why this is called as double sideband suppressed carrier method. Nonlinear or balanced modulators are not part of our syllabus, but just we have to understand what actually they represent. So if you know your physics laboratory in your first year, there you must have studied the VI characteristics of a semiconductor diode. So the voltage and current behavior in forward bias as well as reverse bias is not a straight line. In fact, these are represented by some sharp curves, and these sharp curves occur at the knee voltage of the breakdown voltages, and their behavior is non-linear, and their behavior is given by expression which is in front of you in the red circle. I is equal to AB plus BB square. So such devices in which the current and voltage behavior is non-linear are called as non-linear devices, and such type of modulators are called as the balanced modulators. So in these categories, we have the semiconductor diode, the JFET, the BJT, etc. So now let us move to the next topic of our syllabus, that is single sideband suppressed carrier. So far we have discussed two methods, the amplitude modulation and double sideband suppressed carrier. What is the advantage of amplitude modulation? The advantage is that it is oversimplified, easy. But disadvantage is that it consumes huge amount of power because it is sending the carrier as well as the message signal. The second method is double sideband suppressed carrier. It will have two bands, upper band, lower band, and suppressed carrier means carrier is not sent, so it saves the power, but it has disadvantage that the message signal will be sent twice, once in the upper sideband and once in the lower sideband. So what is the basic problem is that although double sideband suppressed carrier saves the power, but it repeats the information, means information is sent twice. So again there is power loss or information is sent twice, there is no use. If same information is sent twice, then it is of no use. So the next method which improves the amplitude modulation drawback and double sideband suppressed carrier drawback is called as the single sideband suppressed carrier. So it has two main advantages. In this method, the carrier is suppressed means power is saved. Single sideband suppressed carrier, as the name suggests, it will have a single band, either the upper sideband or the lower sideband will be present. So it has both the advantages that the carrier will be suppressed, power will be saved. Second, the information is sent only once and only once, either in upper sideband or in the lower sideband. The third main advantage which differentiates this method from the previous two methods is that due to upper sideband और lower sideband used to कौन सी स्लाइड पे मैं था जब एग्जिट हुआ है
सर? जब एडवांटेज बता रहे थे आप, हाँ यही वाली स्लाइड,
ये वाली थी या ये वाली?
सर इससे 17 वाली थी सर।
77?
हाँ यस सर, यस यही वाली थी।
ओके सॉरी वंस अगेन, आज इंटरनेट कनेक्शन की प्रॉब्लम है, बाकी क्लासों में भी ऐसा ही हो रहा है, दिक्कत हो रही है, कोई बात नहीं, कोऑपरेट। So this the next topic of our syllabus is the single sideband suppressed carrier. This method have three main advantages. The first is it suppresses the carrier, it saves 67% of the power, which is also done by the double sideband suppressed carrier. The additional advantage is that it utilizes only the one band, means either the upper sideband is used or the lower sideband is used. What it means? It means that we are not sending the same information twice in the upper sideband as well as in lower sideband, which we do in the double sideband suppressed carrier method. So in this method, we will send information only either in upper sideband or in lower sideband. This is the second advantage. The third advantage is related to the second advantage. In amplitude modulation method, in double sideband suppressed carrier method, we require the bandwidth equal to twice the maximum frequency present in the modulating signal. But here, as we are sending only information once, either in upper sideband or in lower sideband, so we require half the bandwidth as compared to the amplitude modulation method or double sideband suppressed carrier method. This clearly shows this expression 3.109. The required bandwidth is W hertz. W is the maximum frequency present in the modulating signal, whereas this bandwidth in compare in amplitude modulation method and double sideband the suppressed carrier in the spectrum of method.
सर वॉइस आपकी रुक रुक के आ रही है, क्लियर नहीं आ रही।
अब आ रही है? ओके
यस सर।
ओके, ये लास्ट स्लाइड है, बस इसके बाद आज का टॉपिक खत्म हो जाएगा। So this diagram represents the double sideband suppressed carrier as well as single sideband suppressed carrier. What is the difference in two? This has four diagrams, A, B, C and D. A diagram is for the message signal whose frequency lies between minus W to plus W. The shape of the signal may be sine wave, cosine wave, triangular wave, rectangular wave, square wave, etc. Here it is shown a triangular wave. Frequency varies from plus omega to minus omega. Now this signal is superimposed upon some carrier. This carrier is suppressed in double sideband suppressed carrier method, but it will have the two bands, upper sideband and the lower sideband. Upper sideband have the frequency varying from Fc minus W to Fc plus W. Lower sideband frequencies will have minus Fc plus W, minus Fc minus W. Here the minus sign in front of carrier frequency is just a mathematical representation. In physical world, in real physical sense, the negative frequency does not have any meaning and do not exist. It is simply a mathematical idea, mathematical concept to understand the things. So the figure C and D are for the single sideband suppressed carrier. Here we have a difference from double sideband suppressed carrier figure, that is B. In figure B we have both bands available. But in case of figure C and D, we will have either the upper bands available in upper sideband or lower sideband, or the lower sidebands available in upper sideband or lower sideband. Now what this statement means? This statement means in upper sideband we can divide upper sideband into two parts, the higher frequency from carrier frequency and lower frequency from carrier frequency. Similar, we can divide the lower sideband into two separate parts, frequency higher than the carrier frequency and frequency lower than the carrier frequency. So in single sideband suppressed carrier diagram C, what we have done, we have transmitted only those frequencies which are higher. Let me circle it. The frequencies which are higher the frequency carrier frequency. On the upper side as well as on the lower side part, we are transmitting those frequencies which are higher than the carrier frequency, and in the D figure we are transmitting those frequencies which are lesser than the carrier frequency in the upper part as well as in the lower part. So this is how this single sideband suppressed carrier method is different from double sideband suppressed carrier method. Now the last slide. The advantage of single sideband suppressed carrier is that the bandwidth is reduced because we are sending information only once in the upper sidebands or the lower sidebands. Power is saved because carrier is suppressed. The main drawback of single sideband suppressed carrier is that it is an expensive method and highly complex to implement. Why it is highly complex? Because in this method you require a circuitry to suppress the carrier, and also electronic circuitry to filter the frequencies higher than the carrier frequency or lower than the carrier frequency. So due to the involvement of suppression carrier electronic circuitry and frequency selector, which in which frequencies are selected higher than the carrier frequency in one step, and in another step frequency is lower than the carrier frequency. So these two additional electronic circuitry makes it highly complex as well as highly expensive as compared to amplitude modulation and double sideband suppressed carrier methods. So this is all from my side.